Hello friends, in today's question, two identical balls A and B, each of mass 0.1 kg, are attached to two identical massless springs. The spring mass system is constrained to move inside a rigid smooth pipe bent in the form of circle as shown in the figure. The pipe is fixed in the horizontal plane. The centers of the ball can move in a circle of radius 0.06 meter. Each spring has a natural length of 0.06 pi meter and spring constant is 0.1 Newton per meter. Initially, both balls are displaced by angle theta, which pi by 6 radian with respect to diameter PQ of the circle as shown in the figure, and released from rest. So we have to calculate these three things. First is calculate the frequency of oscillation of ball B. Part B, find the speed of ball A when A and B are at the two end of the diameter. Okay, so this is end. Two end of the diameter of the PQ. What is the total energy of system? So this is a pipe which is, you can see, in the form of a shell, and there are two balls A and B inside the pipe connected by a spring, and PQ is the mean position, that is the equilibrium position, and they are displaced by a angle pi by 6, or we can say theta, and radius is given as 0.06. So this question can be solved in, I think, 2 to 3 different ways. One of the approach is by using the torque method, and the second approach is by considering the, you can say, combining both the masses and combining the spring system, so that this entire system becomes one spring and one mass system. And the third approach is considering the energy of the system. You can solve by using any of these three methods, but the only problem is that in question number, you can say B and C, these are directly or indirectly related with the energy of the system. So it's a much better option to start with energy option, and because energy by default we have to calculate in part B as well as in part C. So we are going to use the energy option to calculate the frequency of oscillation for B, ball B rather. So first of all, we have to find out how the elongation and the compression of the spring is going to take place. So we start from elongation and compression of the spring. Elongation and compression of the springs. So it is given in the question itself that they are at an angle of pi by 6 with respect to the mean position, and let us suppose this we denote as angle theta. So this will be also angle theta. And if x is the amount of displacement for ball B, ball A rather, as well as for ball B, it will be x, because they are with respect to horizontal, they are at same angle. So we can say that for each spring, ball A moves by x equal to r theta. For each spring, when ball A moves x is equal to r theta in one direction, and ball B moves x equal to r theta in opposite direction. direction. So it means the total elongation or compression that will be experienced by the spring connected to ball A will be can be considered into two methods. Yeah, where you can say it can be divided into two parts. You can say total elongation or compression. Experienced by spring connected to ball A will be, now ball A is having two springs, one in the top side and one in the bottom side. Okay. So obviously one will be, we can say, compressed and other will be elongated. So we can say compressed side for the ball A, compressed side for ball A. That is, we can denote with a minus r theta in order to differentiate between compression and elongation. And stretched side for ball B, and that will be plus r theta. So therefore the total change in length, total change in length will be equal to r theta minus of minus r theta, and this gives us 2r theta. So this is a total change in length. Next we are going to find out what will be the energy in each spring. Potential energy in each spring. Potential energy in each spring. We just wrote that each spring will be compressed or stretched by 2r theta. See, each spring is compressed or stretched by 2r theta. Therefore, the potential energy associated with each spring, potential energy for one spring will be equal to half k x square, and x here is the amount of the compression or elongation, that will be 2r theta whole square, and this will be coming as 2k r square theta square. And we have two identical springs, therefore you can say for two identical springs, potential energy total will be equal to twice of, we have 2k r square theta square, and this comes as 4k r square theta square. Okay. Let us call this equation number 1, which we are going to use later on for the part B also. And now we can find out the kinetic energy of the system. Kinetic energy of the system So we can say for the entire system there will be twice of individual kinetic energy. Therefore we can say kinetic energy total will be equal to 2 into half mv square, and this comes as mv square. Equation number 2. Now the total energy of the mass spring system for the entire system. Total energy of the entire system, let us say we denote it as E. So E will be equal to potential energy total plus kinetic energy total. We substitute value. Potential is 4k r square theta square plus mv square, and for the entire system we know that this total energy is always constant. Okay. You can say that for the entire system the total energy is constant. So if E is constant, then its derivative will be equal to 0. So you can say total energy of mass spring system is constant. So which means that our E is constant, or we can say its derivative with respect to time will be equal to 0. So let us suppose this is our equation number 3. So from equation 3 we get d by dt of 4k r square theta square plus mv square is equal to 0. Now we are going to simply derivate it, and we are going to get this as 4k, and this becomes theta 4k 8 r square theta, and this is our d theta by dt, plus we have here 2mv, and dv by dt is equal to 0. So we can take 2 common, and this becomes now 4k r theta, and we make arrangement for this second r with respect to d theta plus mv, and we have dv by dt is equal to 0. And we already know that x is equal to x is equal to r theta. So this gives us that its derivative dx by dt will be equal to r derivative of theta with respect to dt, and dx by dt is nothing but our velocity v. Okay. So we substitute it here, we get 4k r theta and multiply by v, plus we have mv dv by dt is equal to 0, and r theta is equal to x. So we also change it. So we can write this as mv dv by dt plus 4k x v is equal to 0. So dividing entire equation by mv, we get this as dv by dt plus 4k x upon mv multiplied by v is equal to 0. V and V cancels out, and we get this as dv by dt plus 4km x is equal to 0. And velocity we can write our as a in terms of dx by dt. So this becomes dx by dt plus 4k m times x is equal to 0. So we can write it will be now double derivative of x with respect to time plus 4k m x is equal to 0. So from here we can clearly see that this is the equation for SHM. Equation for SHM, this gives us that the time period t capital T will be equal to 2 pi square root of m upon 4k, and we can take 4 outside, so we are going to get this as t is equal to 2 pi upon 2, and we are left with m upon k, and mass is given as 0.1 kg, and spring constant k is also given as 0.1 Newton per meter. So substitute the value, we can write that time, this and this goes, we get pi, and this becomes 0.1 and 0.1, so time becomes pi. Therefore frequency will be equal to 1 upon t, and this becomes 1 upon pi. So we got the first part, that the frequency of oscillation oscillations f will be equal to 1 upon pi. Now we shift to B part, in which we are supposed to find out the speed of ball A when A and B are at the two ends of diameter PQ. So the balls are now end of the diameter PQ. So we already know we are going to use this equation 1, that is potential energy, and so it means potential energy will be equal to total potential energy, and at this stretched position the value of kinetic energy will be equal to 0, and at the mean position the total kinetic energy will be equal to this kinetic energy, and the potential energy will be equal to 0. So therefore we can write that from equation 1, potential energy total was 4k r square theta square. So therefore we can write that potential energy at stretched position let us suppose that is simply denoted as PE, which will be equal to PE total, and this will be equal to 4k r square theta square, and we know r multiplied by theta is equal to x, so you can say but x is equal to r theta, so we can write the potential energy will be equal to 4k x square. And at the stretch position, which is when it is the maximum position then at that particular position the value of kinetic energy is equal to 0. Kinetic energy is equal to 0 at maximum stretched position. Let me write it, maximum. Similarly, we find out that kinetic energy at mean position, let us suppose that is denoted as kinetic energy, and this will be equal to kinetic energy total, and which is from our equation number 2, which is mv square. mv square from equation 2. And at mean position the potential energy is 0. Potential energy is 0 at mean position, because PQ is given to us as a mean position. So we can write that, or we can say we can use conservation of energy. Conservation of energy, we get potential energy at stretched position will be equal to kinetic energy at the mean position. You can say potential energy at maximum stretched position, maximum stretch position is equal to kinetic energy at mean position. So we get 4k x square will be equal to mv square. So from here we can write that our v will be equal to 4k, and this will be m square root and multiply by x. So we can write velocity, this becomes 2 multiplied by x, and x is our r theta, and this becomes square root of k upon m, which is twice, and r is given to us at 0.06. I think, let me check. 0.06, yeah, 0.06 r is given, multiply by theta is given as pi by 6, and k we know is 0.1, and mass is also given as 0.1. So therefore we get velocity will be approximately equal to 0.0628 meter per second. So this is the velocity of ball A. This is the velocity of ball A. And finally, we are supposed to find out what will be the total energy of the system. And we know the total energy of system will be always constant. So it means we can say that total energy of the system, total energy of the system, which we denoted as capital E, and this capital E will be equal to kinetic energy at mean position, or this will be equal to potential energy at stretched position, maximum stretched position. So therefore we can write our energy E will be equal to mv square. Mass is given as 0.1, velocity we just found out is 0.0628 whole square. So we get our energy E will be equal to 3.9 into 10 to the power minus 4 joules. So this is the total energy of the system. Okay. So from here we can also make a conclusion that it's much better to use this energy concept to solve the same question, because it helps in finding out the energy, especially in B and C part. This completes the question. Thank you.